Welcome to ECE 165. This is lecture 3, where we're going to be covering how the operation of the most basic digital circuit works, the inverter. And specifically to do that, we have to start by making sure that we all know and understand the general MOSFET transistor equations and the underlying theory behind them. So let's go ahead and get started. So this is, we're going to start with MOS modeling. This is a section header, so what I'm going to do is I'm going to double box this. And for those of you following along in the textbook, this is starting in chapter 2. So let's start with the general MOS equations. This is something you've all seen before, but we just want to make sure that everybody's on the same page and that we know exactly what we need to use for the purposes of this class. So there are multiple regions of operation for MOSFET transistors, as we know. One of the regions of operation is called the cutoff regime. This is when the gate to source voltage, VGS, is less than the threshold voltage. And in this particular region of operation, we say that IDS, or the drain to source current, is approximately equal to 0. Now, I'm going to put an asterisk here because we will see momentarily. Let's just write that down. We will see this is not technically accurate. Okay, so we'll get into what actually happens in cutoff momentarily. But for now, let's just assume that when we say the cutoff regime, we say that the current is 0. The next region of operation is the linear region. Again, this is something that you should all be familiar with. VGS is larger than VT, and VDS is smaller than VGS minus VT. And we say that in this region of operation, IDS is equal to, I'm going to do this for an Nmos transistor, so it's mu n C aux W over L times VGS minus VT times VDS minus 1/2 VDS all squared. Okay, and then the final and most important regime, at least in for the purposes of analog circuits, is the saturation regime. This is when VGS is larger than VT, so we've inverted the channel. And in this case, we're saying that VDS is larger than VGS minus VT. And in this region of operation, the current drain to source is equal to 1/2 mu n C aux times W over L times VGS minus VT squared. Okay? So we are not using the Kn, Kp formulas. We're going to be a little bit more precise vis-a-vis the device physics. So for those of you who haven't used these exact formulas and instead use the Kp and so on formulas, mu n, this is the carrier mobility. And this is specifically for an Nmos transistor. If it were a PMOS, it would be mu p. This is typically stated in units of centimeters squared per volt second. A little bit of an odd unit there, but it's the convention. And as I said, mu p would be for a PMOS transistor. Now C aux, this is the oxide capacitance. It's effectively the intrinsic parallel plate capacitance between the gate conductor. It's either polygate or in more modern technologies a metal gate. This is given by the dielectric constant E aux divided by T aux for silicon dioxide, which used to be commonly used as a gate dielectric. Epsilon aux was approximately equal to 3.9 epsilon 0. Okay, where that's the basic dielectric constant. Now, typically, we have a difference between Nmos and PMOS currents. We say that IDS for an Nmos divided by IDS for a PMOS is typically somewhere on the order of 1 to 4. Okay, now that's a little bit of a broad range. We say that in older technologies, for example, 0.35 micron, it is closer, this ratio is closer to the high end. In newer technologies, and for example, let's say 28 nanometer, although now we're all the way down to 7 nanometer, it is closer to 1. Okay, so there's a few reasons for this. I mean, the intrinsic carrier mobility between electrons and holes is different depending on the doping and the materials and so on. And then it also depended on what the gate materials were. Is it a poly gate? Is it a metal gate? Is there buried conduction or not non-buried conduction, and so on. So there's a lot of device physics reasons why all of this happens. But for the purpose of this class, we don't want to make things too complicated. We want to be able to do hand analysis. So we're going to say in this class, and by this class I mean the entirety of the course, for hand analysis only, we will assume that the IN over IP ratio is equal to 2. So kind of somewhere in the middle of that range. Now this will not be true for the 45 nanometer process that we're using in this course. So if you go ahead and do your simulations, you will find that the ratio of an NMOS to PMOS for current is not equal to exactly 2, although it'll be somewhat close. Okay, so it's a reasonable assumption when we are doing analysis, particularly hand analysis. So given this formula, particularly the subthreshold or rather the saturation formula, IDS is equal to 1/2 mu n Cox W times over L times VGS minus VT squared. So we're designers. We like to know what we can do with our transistors. So which parameters do you, as a circuit designer, as a digital designer, control? Okay, so let's say we want to adjust the power or performance of our circuit. What do we as designers have access to? Okay, can we change mu n or mu p? Well, no, we can't change that. That's set by the fabrication process, the materials employed, and so on. So we as designers who are designing circuits really have no control over this. What about Cox? Can we as circuit designers control this? Well, the answer here is also no. In the sense that, the transistor is what the transistor is. Somebody at the foundry has decided what the thickness of the oxide ought to be, what the materials in that oxide are. As I mentioned in the previous slide, a lot of materials in classic CMOS technologies use silicon dioxide. In more modern processes, they've been shifting to high K dielectrics. That might be a buzzword you've heard thrown around in the literature or in the industry. Things like hafnium dioxide and so on are interesting choices. Just basically have a much higher dielectric constant so that we can make the gate thicker for reasons that will become apparent soon. But really, as a circuit designer, the transistor is what the transistor is. Now, there is a caveat to this. Maybe I'll put a little asterisk here, in the sense that as a circuit designer, we are typically given a couple different transistor flavors. For example, in a lot of design kits, we have our core transistors. These are the low voltage, 1 volt, say, transistors. They're designed to operate fast and for digital logic, RF, and so on. These are our main transistors. But 1 volt is usually not enough to interface with the outside world, so we often have a second class of transistors called thick oxide or IO transistors. These are devices with obviously thicker gate dielectric oxides, which allow them to operate at higher voltages. This is useful for IO. And so from that perspective, we do have maybe a choice or two of different Cox values, but really for digital design, we don't have any control over this. What about the threshold voltage? Well, again, we don't really have control over this. I'm going to say limited. I'm not going to say no. I'm going to say limited. Limited in the sense that most process design kits have various different threshold voltages available, or various different transistors that have various different threshold voltages available. You might have an HVT device or a high threshold voltage device. You might have an LVT device or a low threshold voltage device. So you have maybe a small handful of different transistors that you could choose from, and therefore, change the threshold voltage. Now, at the same time, we have an effect that we'll study, and perhaps you should already know about, called the body effect. And the body effect is a nice way that we can actually dynamically modulate the threshold voltage of a transistor. Now, it's not always conveniently accessible, particularly to Nmos transistors, but it is something that possibly we do have access to as a digital designer. So that's almost all the parameters in those formulas we showed above. The last remaining one is the W over L ratio, and yes, this is our main mechanism of control when we are designing circuits, by controlling the W over L ratio. All right, so with that out of the way, we now are all on the same page with what formulas we have available to us, and we'll use these formulas in this class. Let's go ahead and discuss the Cmos inverter. So we know from our introductory classes what logic gates functionally do. How do we build a logic gate out of transistors? Obviously, we need to be able to do this if we want to build actual digital circuits that actually operate. So the simplest way to do this is the following circuit. This is the simplest logic gate we can build. It's a Cmos inverter. Okay, and all we do here is we take two transistors and we stack them on top of each other. One is a PMOS and one is an NMOS transistor. So let's imagine this is the input voltage and this is the output voltage of this so-called inverter. All right, let's go ahead and draw the voltage transfer curve of this CMOS inverter. So I'm going to plot V in on the x-axis and V out on the y-axis. All right. So this is actually a very good exercise for everybody to do. I want you to think very carefully about what this looks like before I even draw it. So perhaps even pause your video, see if you can try and guess what this curve is going to look like. Okay, so go ahead and do that now. So I'm assuming you've paused and you've tried this. If not, that's really too bad. I wish you would have. But let's go ahead and complete this now. So let's just think about this from a fundamental perspective. Okay, so what happens when V in is very high? Okay, when V in is very high, let's say it's approaching the value of VDD here. What mode of operation is the NMOS transistor in? Okay, so we would imagine that the NMOS transistor, if Vin is very high, VGS is very high. That means the NMOS transistor is definitely not in the cutoff regime. It must be either in the saturation regime or the linear regime, because VGS is much larger than VT here, assuming VDD is larger than VT. Now, what should Vout be if Vin were high? If this were functioning as an inverter, then if large Vin voltage came to the input of the circuit, then the opposite voltage must be coming to the output of the circuit. So Vin should be very low. Okay, so perhaps your first inclination is to say, hey, VGS is very large, this transistor is clearly on, it's going to be in the saturation regime. Well, unfortunately, that's not correct. It's not correct because Vout is very small. Therefore, VDS of this transistor is very small. If VDS is small, it must be operating in the linear regime. Okay, so what that means is that when Vin is large, Vout is rather small. Okay, now what I'm going to do is I'm going to add a little legend here. The legend will be PMOS mode of operation and NMOS mode of operation. So we just finished discussing that the NMOS transistor is going to be in the linear regime when Vin is large. Now what about the PMOS transistor? What mode of operation is the PMOS transistor going to be in? Well, if Vin is close to VDD, that means VGS, or equivalently VSG for a PMOS transistor, if you prefer to think in that regime, or that way, is close to 0. So we're going to say that it doesn't matter what VDS is, the PMOS transistor is off. It's in the cutoff regime. Okay. All right, so now let's do the same exercise when Vin is low. When Vin is close to 0, we're going to say the NMOS transistor is near, the VGS of the NMOS transistor is near 0, and so therefore the NMOS transistor is probably going to be in the cutoff regime. If this were functioning as an inverter, if Vin is 0, then Vout ought to be close to VDD if this were functioning as an inverter. So we should be operating somewhere up here. And just as we said that for when Vin was large, the NMOS was in the linear regime, we can say the same thing about the PMOS transistor here. So its VSG is very large, so therefore it's definitely on, but its VDS is very small, so therefore it's operating in the linear regime. And as we discussed, the NMOS transistor is in the cutoff mode. So when Vin, let's recap. When Vin is low, Vout is high. When Vin is high, Vout is low. Okay, so that's exactly the behavior that we would want from an inverter. We put in one voltage, we get the opposite voltage coming out. Keeping in mind that a logic 0 in this type of circuit is represented by a 0 voltage, and logic 1 is represented by a voltage near VDD. Now, in a perfect world, these two different levels here would just instantaneously swap once we cross the inverter threshold voltage. In actuality, that doesn't happen. There's going to be some kind of gradual change between these two different states here. Okay, so I want to label one state here. This is what we're going to call VM. Ideally, this happens at VDD over 2. Ideally, oops, let me spell that correctly. And likewise, this would happen at VDD over 2 at the output if we were to size our device perfectly. Okay, so let's think about the region of operation in these areas here. Okay, so let's start here. So in this particular case, we're saying that Vin is still relatively low, but perhaps now we have exceeded the threshold voltage of the NMOS transistor. Okay, so if we exceeded the threshold voltage of the NMOS transistor, VGS is larger than VT in this particular instant. What about VDS? Well, VDS of the NMOS transistor is still rather large because Vout is still rather high. So therefore we say that the NMOS transistor is in the saturation region. Likewise, VSG of the PMOS transistor is still relatively large, so it's still turned on, but VDS is still pretty small because Vout is still pretty close to VDD. So we say that the PMOS transistor is still in the linear regime. Okay. Now then we'll travel to this kind of region around the middle here where Vout is close to VDD over 2, ideally, which means that both transistors are on. Both transistors have appreciable VDS across them. So we're going to say both of them are in the saturation regime. Okay, and for those of you who are interested in analog circuit design, this is actually a perfectly good amplifier. both transistors are operating in the saturation regime, we actually get double the amount of transconductance that we would normally otherwise get with a single transistor operation. Okay. We're not going to study amplifiers in this course. It's just interesting observation. And then in this regime, it's the opposite of the other portion of the regime here. So in this case, we say V in is rather large, so the Nmos transistor is definitely on. And VDS of that Nmos transistor is a little low, so we're going to call it in the linear regime. Whereas we're going to say VSG for that PMOS transistor is still appreciably large, and so it's still on. It hasn't cut off yet. But we have a very large VDS across it, and so we say that it is in the saturation regime. Okay, so that now completes the voltage transfer curve. Okay, let me just add one more note. VM here, this is what we call the inverter switching threshold. So we say beyond VM, we have gone from a logic 0 to a logic 1. So let me ask a question. How do we design VM to be, say, equal to VDD over 2? So we said, ideally, if we're designing a nice inverter, the VM should be equal to VDD over 2. So how do we as designers do this? How do we make sure that this circuit will switch when will cross through the VDD over 2 point at the output when the input is VDD over 2? This is especially difficult because we know that the Nmos and PMOS transistors have different characteristics. Mu N is not equal to mu P, for example. So the answer to do this is, well, you have to adjust. We do this by adjusting W over L for the PMOS and W over L for the Nmos until Vm is equal to VDD over 2. And you're going to do an exercise like this in your first lab. Okay, so what we're going to do is we're going to adjust we're going to probably set Vn, and then we'll adjust Vp until we get the appropriate voltage of VDD over 2 at the output when the input is equal to VDD over 2. So what that voltage transfer curve told us is that, you know, we're building digital circuits. We want a 1 to be represented by VDD. We want a 0 to be represented by ground, but we actually live in an analog world, and that's not perfectly the case all the time. So this is why we have to talk about a topic called noise margin. And as I mentioned, logic 1 and 0 are not necessarily represented by exactly VDD and ground, but rather by ranges around these values. We use the following definitions to determine the margin with which we can operate. Okay, so let's imagine we have two inverters, one driving the other. And I'm going to just draw a little picture here. And this picture represents the range of possible values that the circuit could have. Okay, so this is ground at the bottom and VDD at the top here. Okay, so what we say is at the output of this inverter, we definitely want the VDD to be within some range up here to represent a logic 1, and the output to be within some range here to represent a logic 0. And in between here is no man's land. If the inverter is working properly, it will never get within this region. We call this the V out high, and this the V out low. Okay, so an output high voltage has to be at least as high as VOH, and an output low voltage has to be equal to or lower than VOL. Now we can draw a similar picture for this other inverter over here. Okay, now in this case for the input, we're going to make it a little bit more generous. We're going to say this is the no man's land for the input into this inverter. And we want to make sure that the input is at least higher than VIH, or V input high, in order to represent a logic 1, or lower than VIL in order to represent a logic 0. Okay, so basically what this allows us to do is set up a little bit of margin. Okay, so as long as our signal is output higher than VOH, then we can with good certainty ensure that it's larger than VIH with some noise margin on the high end here. Okay, and likewise we have some noise margin on the low end over here. Noise margin low. Okay, so we say VIH is the minimum high input. VIL is the maximum low input. VOH is the minimum high output, and VOL is the maximum low output. So we say the noise margin low is equal to VIL minus VOL, and the noise margin high is equal to VOH minus VIH. Okay, now there are varying definitions for how to define what VIL and VOL and so on are. This is one that we're going to use for the time being for the purposes of discussing how an inverter works. Again, I want to emphasize that there's many other ways that one could make these definitions, but this is, I think, a reasonably good one. So we're going to say that when the slope of this curve, and sorry, let me label the axes. We should never draw a plot without labeling the axes. The slope at which this curve is equal to -1, we're going to say is equal to VOH. Okay, and likewise over here, the slope where this is equal to -1, we're going to say this is VOL. Okay, and then we're going to drop down on the vertical axis over here and say that these points correspond to VIL and VIH. Okay, and so what we'd say is the region in here, this is the bad region. And what we mean by that is if the input falls here, we may not regenerate to a correct output or correct value at the output. Okay, So as I said, this is just one possible definition. VOL, VOH, sometimes is just the minimum or maximum possible output voltage. So just make sure that you know, when you're discussing VOL, VOH, VIH, etc., that you just make sure that you're aware of what nomenclature is being used. Okay, so now that we have a better understanding of the inverter and how the relative or relevant MOS equations correspond to that voltage transfer curve, let's go ahead and talk about some of the non-idealities of our circuit. So we're going to talk about MOS non-idealities. And you might think, you know, I've heard about these MOS non-idealities all the time. They're just kind of annoying. Can we just not study them? And unfortunately, there's a reason we study these things. They are important effects. Some of them we can actually leverage to our advantage. A lot of times they just really hurt. But let's see what we have here as they relate to digital circuits. So the first one we're going to study is the body effect. Okay, this is one that you should already know about. In this case, we say that the threshold voltage of the transistor is not some static parameter, but rather it is some static parameter plus an additional term, gamma, times the square root of phi s plus VSB plus, or rather, sorry, minus the square root of phi s. Okay, so this is the definition of the body effect. This is the classic definition. Things are, of course, far more complicated in reality, but I think this is a nice, good first-order model for us. Now, the key here is we are saying that the threshold voltage now depends on the square root of the source to bulk voltage. Okay, so if we can either modulate the source voltage or the bulk voltage, this is our way to control the threshold voltage of our transistor, potentially dynamically. All right, so let's just describe a few of these other things here. VT0 is equal, this is equal to VT when VSB is equal to VB, so when there's no explicit bias applied across the device. Gamma is the body effect coefficient, and it's typically let's say somewhere between 0.4 to 1 root volts. Okay, so yeah, a little bit of a weird unit there. And phi s is the surface potential. And there's all sorts of interesting semiconductor physics going on here. We'll just call it a process parameter that will be given to you by the foundry. We're not going to get into any more detail than that in this course. Okay, so the body effect is annoying. The threshold voltage is not constant. But interestingly, this is actually an opportunity for us as circuit designers to possibly leverage the body effect in order to dynamically change the threshold voltage, which has some interesting benefits. Okay. The next non-ideality I want to talk about is channel length modulation. Okay, and this is something that you should have already learned about in ECE 102 or an equivalent class. So if you want more details, go back to your equivalent class about this. The base punchline is that IDS prime is equal to IDS times 1 plus lambda times VDS. Okay, and the basic idea here is that when the drain to source voltage starts to get very large, we start to pinch off the channel, and what that does is effectively cause the channel to shorten, and there's all sorts of interesting effects that happen as a result. Again, we're not going to get into all of these details here. Let's just say that this is the formula that you would use when we include the effect of channel length modulation. So the body effect and channel length modulation are probably non-idealities that you've seen and talked about before. This next one may be one that you've not seen or discussed before. We're going to lump them into two things together here. So there's something called mobility degradation and velocity saturation. These aren't always covered in the more introductory courses, so let's talk about them. Now, one note I want to make, and unfortunately this is going to get extremely confusing for everybody in this course, is we use the word saturation in multiple different contexts. Okay, so when we are talking about velocity saturation here, we are not talking about the saturation region. There's a separate region that we're going to consider called the velocity saturated region. This is going to get even more confusing when we start talking about the next non-ideality, where there's another region of saturation. So whenever you use the word saturation, make sure you are being very clear about what you mean to make sure that there's no confusion. Okay, so mobility degradation and velocity saturation, what does this all mean? So let me write a little paragraph here. In deep submicron processes, and this is perhaps, I don't know, it depends what people mean by deep. Let's say below 180 nanometer. Let me just write that a little bit more cleanly. Nanometer. In deep submicron processes, channel lengths are so small such that the lateral electric field across the channel which is E is equal to VDS over L. So remember, as we scale down in process technologies, as we go from 180 nanometer to 90 to 45 to 28 to 16 to 7, etc., that key number there is representing the L. So L is continuing to shrink. As L shrinks and VDS stays roughly constant, it hasn't really changed too much from 1 volt, then the electric field across the transistor starts to get very big. Okay, so we're saying the lateral electric field across the channel is so large that carrier velocity I'm going to attempt to use a lowercase v. I'll put a little doodad on the end of the v here and make it a little smaller than my uppercase v's to distinguish between voltage and velocity. Again, please try to be as clear as possible when you do your writing in this context. The velocity, which is given by the mobility times the electric field, ceases to increase linearly with voltage. So normally we would expect that as we increase VDS across the device, we would get a proportionally linear increase in the carrier velocity. But when the length gets so short and the electric field is so large, there's all sorts of other physical effects that start to happen here, and we no longer get this linear increase. We call this velocity saturation. Okay. Now, another kind of related effect also happens here. We talked about the lateral electric field, but now at high vertical electric field, electric field strength, which is in this case given by E is equal to VGS divided by the gate dielectric thickness. What we say in this situation is that carriers scatter more frequently slowing their progress. We call this mobility degradation. Okay, so there's two different effects here. Both have to do with when we have large electric fields across the device, which generally happens when we are in a deeply scaled CMOS process. And both of these things basically slow down the charge carriers in the device. Okay, this is a very quick explanation. If you want to read more, I suggest you take a look at the textbook. They have a much more detailed explanation. Of course, you can get into all the device physics that you want to really understand this in great depth. We don't have time to do that in this class, so I'd recommend checking out section 2.4.1 in the West and Harris book, or section 3.3 in the Rabai, Chandrakasan, Nikolic book. Okay, so this is the basic introduction. I'm going to say in general, assume that we are dealing with velocity saturation and I'm going to kind of lump in velocity saturation with mobility degradation. They are different effects, but that's kind of what we're going to do here. In general, assume that we're velocity saturated when VDS is larger than VDSat, where VDSat is equal to L times the saturated velocity, so a little wiggle on the end of that V there, divided by mu n, or mu p if it's a PMOS. Okay, so we say that Vsat, the saturated velocity for an Nmos transistor is approximately 10 to the 7 centimeters per second for Nmos, and approximately equal to 10 to the let me get this more correct, 8 times 10 to the 6 centimeters per second for PMOS. So if we go ahead and assume that the device is velocity saturated when VDS is larger than VDSat, where VDSat is given by what we showed on the previous slide, then what we can say then is that the drain to source current when we are saturated is given by W times Cox. Note there's no L here, I haven't forgotten it, times the velocity, the saturated velocity, times VGS minus VT minus 1/2 VD sat. Okay, So this is the velocity saturation formula. Now this is first order and empirical and so on, but it's a reasonable approximation for hand analysis. Now one thing to note, it is not squared. Okay, we're used to having our velocity, or rather our saturation device, have a square relationship with VGS between IDS. In this case, it is not squared, it is linear. Now this is a little bit of a clunky formula to carry around because there's no L, there's this velocity saturation, or the saturated velocity parameter in here. So what I'd like to do, and I'm going to deviate a little bit from the West and Harris book in this case, is I'm going to introduce a unified model for hand analysis. This actually follows the derivation in the Rabai, Chandrakasan, and Nikolic book. So in this unified model, I'm going to say that IDS of the transistor is going to be equal to mu n Cox, again doing this for an Nmos transistor, times W over L times VGS minus VT times a new parameter I'm going to call Vmin minus 1/2 Vmin squared. And then I'm going to include the channel length modulation parameter here as well for completeness. Okay, so far this actually kind of looks like if Vmin were equal to VDS, this would be identically the linear regime formula. So we can say where Vmin is equal to, as the name implies, the minimum of these parameters, either VGS minus VT, or VDS, or VD sat. Okay, so maybe let me box this in red here. So if you go ahead and plug in VGS minus VT into this formula, what you'll find is you will get the normal saturation expression. If you plug in VDS, you will get the normal linear expression. And if you plug in VD sat, you'll actually get the velocity saturation expression that we just showed above. Okay, so this is a general formula that works for all three of these regions of operation, provided that VGS is larger than VT. I should perhaps specify that for VGS larger than VT. Okay, so let's go ahead and plot what these effects may have. And the astute of you may notice that we're kind of breaking one of the assumptions that I had listed earlier, namely that we are saturated when VDS is larger than VD sat. If you look at these formulas carefully, we'll get to that in a moment. So first I want to make a plot of IDS versus VGS. Okay, so normally this is supposed to be, 0 until we cross the threshold voltage, and then we are quadratic. Okay, this is what we'd call the normal saturation regime. Okay, and then this here is approximately the threshold voltage. So below that we're in the cutoff regime, and then after that we are saturated. Now in actuality, what happens if we are velocity saturated, then what ends up happening is this basically becomes a straight line. Okay, so this is velocity saturation. This implies that indeed we are operating as a linear mode device rather than as a quadratic mode device. This is unfortunate because this means that for the same amount of VGS, if we're using this in a velocity saturated device, a short channel device, we're going to get less current than we would have otherwise gotten if we didn't have to include the effects of velocity saturation. Okay, I'm going to make this plot a little bit bigger. So what I'd like to plot now is IDS versus VGS. Okay, so this is, the previous plot was IDS versus VGS, and I'm sorry, I want to plot this not versus VGS, but versus VDS. Okay, so this is versus VDS. Now normally we expect this plot, perhaps I'll use green here. Remember, we start off in the linear regime, and then eventually we kind of saturate. Maybe there's a little bit of channel length modulation going on here, etc. It usually looks something like this. Now, when we consider the effects of velocity saturation, as we were to have increased VGS, we were supposed to get a quadratic increase in the difference between these plots. But in velocity saturation, it's only a linear increase. Okay, so that's the key difference here. The other thing to note, let me just complete this family of curves here, is that we did say that the device is supposed to be velocity saturated when VDS is larger than VDSat. But if you go ahead and plug the results into this formula, you'll find that VGS minus VT could still be positive and obviously in the above threshold regime, but VGS minus VT could be smaller than VDSat, which implies that we could still be in the saturation regime even for very large values of VDS per that formula. That doesn't really jive with what we had on the previous slide. It turns out that it's far more complicated than what is shown in these formulas, but per modeling efforts and so on, we've kind of said that, well, this is actually a reasonably good approximation, or a reasonably good formula for first order analysis. So what we can do is we can split the regions here kind of as follows. On this side, let me dial this in yellow here. Actually, that doesn't look super good, but anyways, we say that this is the linear regime. Okay, this is this line here, and I'm sorry, that red line should have been a straight line going up. This is the VDS equals VD sat line. So anything to the left of this line, provided that, and I should perhaps specify this line, this is VDS is equal to VGS minus VT. Everything to the left of this red line is the linear regime of operation. Anything, anything above this portion of the red line we would call the velocity saturated regime. And anything below this line is called the saturation regime. And this line here is when VGS minus VT is equal to VD sat. Okay, so again, that doesn't quite jive with the text that we had on the previous slide, which said that velocity saturation occurs when VDS is larger than VD sat. But we observe in experimental data that when VGS minus VT is rather small, we don't get as saturated of a velocity as we would otherwise expect. It turns out that maybe there's also some mobility degradation effects going on and so on. It turns out it's rather complicated. So for the purposes of this class, I'm going to ask that we use this boxed formula when we are doing our hand calculations. Empirically, it's actually pretty decent of an approximation. So for the purposes of this class, let's continue using this formula. All right, so the next item that I want to start discussing is a very important one, one that is used to good effect in analog circuit design, one that is nominally detrimental to digital circuit design, although we could potentially use this mode of operation as well for specific functionality. And this method, or this non-ideality, I guess, is what we call subthreshold conduction. Okay, this is really important to study and make sure that we understand this. It is a very important part of digital circuit design today, and frankly, it's an important part of at least low power analog circuit design as well. And I don't believe this is typically covered in most other courses. So what is subthreshold conduction? Well, first let's just say that the cutoff region of operation is a mathematical abstraction. Okay, so it doesn't actually exist. In reality, there are small but very important quote-unquote leakage currents that flow through the device when the transistor or the device is quote-unquote off. Okay, so what this means is we have the device that VGS is, say, for example, 0. We should have ideally no current flowing through the device. But in actuality, it's not a perfect switch. It's not like when we put VGS as 0 that there's 0 current flowing through the device. There is some amount of current, and that current flows by a number of different mechanisms. The predominant one is called subthreshold conduction. It is also called weak inversion. And the name is effectively as it implies, where the channel is not fully inverted, i.e. VGS is not large enough to invert the channel, and so it's not larger than VT. But perhaps there is a little bit of a channel still there, or maybe it's weakly inverted, so this is also sometimes known as weak inversion, and can actually be a very useful region of operation, particularly if we're interested in very low power design. For low power designs. And this is true for both analog and digital circuits. So let's go ahead and write down the formula. IDS is equal to, oops, color change there, is equal to IDS 0 times E to the VGS minus VT plus eta VDS minus K gamma VSB. All of this is over N phi T times 1 minus E to the minus VDS over phi T. Okay, so everything clear? Probably not. Let's go through and identify each of these parameters individually to make sure we understand what's going on here. So first of all, IDS 0, oops, this is the current when or at VGS is equal to VT. So if we put VGS right on the threshold, we get a current that we call IDS 0. It's approximately equal to, and this is a bit of a heuristic, mu Cox W over L times phi T squared times E to the 1.8. Okay, so obviously, some approximation here. Okay, in the exponential term, we have VGS minus VT. Both of those are clear. We have this eta term. This is called the DIBL, DIBL coefficient. That stands for drain-induced barrier lowering. We'll talk about this later. Okay, so for now, let's ignore it. And this K gamma VSB, as you can imagine, this is modeling the body effect. Okay, and then this last term, I want to specifically call this out here. This basically just says that if VDS is 0, then E to the 0 is equal to 1, 1 minus 1 is 0, so the whole current expression goes to 0. And so what this says is that leakage is equal to 0 if VDS is equal to 0. Okay, so this makes sense actually. If there's no voltage across the device, we shouldn't expect any current to flow across it, right? Otherwise, maybe we've invented a perpetual energy machine. And then it increases to its quote-unquote full value when VDS is much larger than phi t. Okay, so what I mean by that is if VDS is much larger than phi t, then this is e to the minus a big number, or conversely, it's 1 over e to the power of a big number, which basically just means that second part of this term here goes to 0. 1 minus 0 is just 1, and so this thing kind of just goes away. Okay? All right, a few other things to make note of. Phi t is the thermal voltage. It's equal to kT over Q, and it's approximately equal to 25 millivolts at room temperature. Okay, so what that means is that we say that the leakage is full, if you will, making an extra note over here, when VDS is larger than approximately 100 millivolts. Okay, so what's really interesting here is that this basically means that the transistor gets saturated within subthreshold. Okay, so if you look at the expressions for IDS term, the only part that has a VDS component is in this second bracket here. Okay, and once VDS is larger than about 100 millivolts, the device no longer responds to VDS changes. So that sounds like a saturation regime. And indeed that's the case. Okay, so this is where it gets confusing. We have saturation in the normal sense of the word. We have velocity saturation. And now within the subthreshold regime, we also have a saturation mode. Okay, so yes, it does get confusing. So whenever you talk about my device is saturated, please make sure you indicate what type of saturation you are referring to. Is it normal above threshold saturation? Is it subthreshold saturation? Is it velocity saturation? Okay, these are important things to make sure that you make a note of. Okay, and the last note that I want to make here is N. That's the only term I think we haven't defined yet. This is what we call the subthreshold coefficient. Okay, typically varies from something like 1.3 to 1.8, let's say, okay, in CMOS. Interestingly, N equals 1 for a BJT, or in other words, it doesn't have this additional subthreshold coefficient. And there's a very good reason why that would be the case from a transistor physics perspective. Okay, so now that we understand that subthreshold is a mode of operation and actually happens, let's go back and revisit our current versus gate to source voltage curves. So I'm going to plot IDS versus VGS. So remember, let's imagine that this was the threshold voltage here. What we assumed before is that prior to VT, current was 0. Now we know that there's a subthreshold kind of exponential behavior going on here. And so we know that there is some amount of current, but it's still low. So, maybe the current will look something like this, and then it'll go up quadratically here. So remember, IDS over here, that's a very poor S. IDS is proportional to VGS, I guess, minus VT squared. Right. Now, we also did say that if the device were velocity saturated, that it would be proportional to VGS minus VT to the power of 1. Okay, this is when it's velocity saturated. And this green curve is when we are just normal saturated. Okay, but this picture doesn't really give us a good idea of what's going on in the subthreshold device. So what I'd like to do is I'd like to do that same plot, but in this case I'm going to plot it on a log scale. Okay, so I'm going to plot the log of IDS. Now we know that the subthreshold expression is an exponential expression. We didn't really hit on that, but that just means, you know, this is a very steep slope. This is a very steep curve. And an exponential in a log domain plot, as we know, is a straight line. So it'll look something like this until we hit the threshold voltage, VT, at which point it starts to taper off in, you know, our exponential form here. Okay, so this is a straight line in a log domain plot. So we say, just actually before I do that, let's just say that anything to the left of here is what we'd call subthreshold, and anything to the right of here is above threshold. And when I say sub-VT, I'm thinking in my mind sub-threshold, not sub-VT. Now this is a straight line in a log domain plot. A straight line we know we can assign a slope to. Okay, so we say that S, let me do this in black here, S is what we call the sub-threshold slope. And it is equal to n phi t times the natural log of 10. This can be derived directly from the expression, which is equal to kt over q times n times the natural log of 10. Okay, and note that this is slope, but it's in units of millivolt per decade. Okay, normally when we think about slope, we think about it in delta y over delta x. In this case, we're actually doing the reciprocal, where delta x over delta y. So for example, if n equals 1.5 and we're operating at room temperature, then the slope is equal to 90 millivolts per decade. That would be at room temperature. So I have a question. Is a large or small n better? And I'm going to ask this ceteris paribus, which is Latin for all things being equal, all else being equal. Okay, so do we want a small n or a big N? Normally we like big numbers, but let's think about this. What does the slope represent? The slope represents the steepness of the transition from above threshold to subthreshold, or from on current to off current. Now, if we're building digital logic, it turns out that we tend to want a really steep slope. That means there's a big difference in the on current versus the off current. This is exactly what we want when we're building digital logic gates. Okay, so that means we want a steep slope. A steep slope means that S, because it's the reciprocal of the normal slope factor that we're used to seeing, needs to be a small number. This means that the answer to this question is we want n to be small. Ideally, or the lowest it could possibly be, is equal to 1. And the reason we like this is because it gives us a large I on over I off ratio. Okay, this is very good. Now, interestingly, one question that may arise here is that the best n for our CMOS logic is 1. And as I mentioned previously, a BJT has by default an n equals to 1. So does that mean a bipolar transistor is better than a MOSFET? It's an interesting question, actually. From this very specific perspective, yes. It has a steeper, what we would call a subthreshold slope, although in a BJT it's not actually a subthreshold operation, but you get the point. It has a steeper transition from on to off. That is actually good for digital logic. Now, of course, we don't use BJTs all the time when we're building digital systems for a very good reason. One of those reasons is that, well, they have this current that has to go through the base of the device, which doesn't nominally exist in a CMOS transistor. In addition, we've gotten very good at miniaturizing each CMOS transistor such that we can fit a huge, very high density of transistors in a small area. And for these reasons, CMOS transistors have won the digital logic compute space by far over any bipolar type of technology. Another interesting question to ask is subthreshold conduction better at higher or lower temperatures? I'm going to leave that one for the viewer to decide for themselves, but I would like you to think about it. In above threshold, do you get higher or lower drain current at high temperature? And in subthreshold, is the answer the same or is it different? So think about that. So now I'd like to move on to a few of the remaining non-idealities. There's another one called junction leakage. Okay, so basically what this means is that we have reverse biased diodes that have current, or rather diode currents, okay, that leak. Okay, so to understand this, let's again draw a cross section of our MOSFET. Use a few different colors here. So that's our gate. Here's our gate dielectric. This is our source and drain regions here. Let's draw an Nmos transistor. So this is an N plus region, N plus. P substrate over here. And this is the source, the drain, and the gate. Okay, so it turns out that we do have these PN junctions that form between the P substrate and the doped regions forming the source and the drain. And between these diodes, now normally, if you recall, the P substrate is always grounded, and the source and the drain must be at a potential that's at least higher than ground to make sure that these diodes don't turn on themselves. So this means they're reverse bias, and a reverse bias diode will have some current, I junction current, that flows through it. Okay, we can model I junction as equal to, well, it's a diode current expression, IS times e to the VDB or SB, depending on whether or not we're talking about the source or the drain, minus 1. Okay, so that's a reasonably good model for our reverse biased diode currents. Now it turns out that these currents aren't super big. We tend to be more dominated by the subthreshold current that's flowing through the channel. So when we're doing hand analysis, we typically don't worry too much about junction leakage. I just want to introduce it to make sure everybody knows about it. There's another non-ideality, one that we actually mentioned earlier, DIBL, okay, which stands for drain induced barrier lowering. Or nicely known as DIBL. Okay, and what this implies is that a high VDS creates an electric field that can affect the threshold voltage of the device. Okay, so what we say is that VT is equal to VT0, the nominal threshold voltage, minus eta times VDS. Okay, eta is typically somewhere around 100 millivolt per volt. It's a dimensionless quantity and is referred to as the DIBL coefficient. So what this does is it causes IDS to increase with VDS in saturation. Okay, so normally this is not a problem for digital CMOS circuits. CCTS is just my abbreviation for circuits. I should clarify this point. It's not a problem for normal circuits at nominal supply voltages. It turns out it can be very important in subthreshold. Just take a moment to think about why that might be the case. If IDS, or rather, if VDS in subthreshold changes, this will cause a change in the threshold voltage. Now, if you'll recall, subthreshold conduction is now exponentially dependent on the threshold voltage. So if you could just draw a little quick plot here, I'm going to plot IDS in log scale versus VGS. And if, let's say the supply voltage is 2.5 volts, we get some sort of curve that looks like this. Rather, actually, let's do this at 1 volt. Now, if VDS happens to change, and therefore we get a change in the threshold voltage, then what's going to happen is the threshold voltage will lower as VDS increases. And so as a result, we're going to get a change in the threshold voltage, which might change how this plot actually looks like. Okay, and because we're in a log scale, this could be orders of magnitude. Okay, so you really do have to be careful about what this might look like in terms of subthreshold. So there's just a couple more non-idealities I want to cover before closing out the lecture. One of them is gate leakage. Okay, so we talked about subthreshold leakage, we talked about junction leakage. How can there be leakage through the gate? The gate is made of a dielectric, right? There's no way that current can flow through that. Well, it turns out that that's not exactly the case. So we could potentially have quantum tunneling of electrons through the gate oxide. Okay, so there's in very scaled technologies, the gate oxide was becoming extremely thin when we were using silicon dioxide as our gate dielectric material. It's so thin it was in kind of the 45 nanometer process technology node range. It was literally only a handful of atoms thick. If it's only a handful of atoms thick, there's a non-zero chance that electrons could just quantum tunnel right through the gate into the channel of the device. This is, a problem if you're not aware of it. So you do have to be aware of this. In fact, I had some colleagues of mine who designed some chips in 90 nanometer, and they had a lot of extra silicon area available, and so they decided to make a large network of decoupling capacitors using MOS capacitors, basically using a MOSFET as a capacitor. This is normally a great idea. If you have extra area, decoupling always helps. However, they didn't account for in their simulations the effects of gate leakage. So as a result, when the chip came back, they measured a much larger leakage current in their design than they otherwise expected. And as it turns out, the culprit was gate leakage because there was such a large area of MOS capacitors being used for decoupling, there was actually a huge amount of gate leakage happening in that chip, so much so that the standby performance of that chip was quite a bit higher than they had designed for. So we say that this is important for 90 nanometer technologies and below. Now I would say that as the industry transitioned from silicon dioxide as a gate dielectric to a high K dielectric like hafnium dioxide or something like this problem has kind of improved, or it's gotten less severe. I believe, if memory serves correctly, that happened around the 28 nanometer or so node. So we can model gate dielectric. It is the width of the device times the area times VDD over Tox squared times e to the minus b Tox over VDD. A may not be the area, actually. It's a parameter. This formula is available in the textbook with more explanations and details. For our purposes, we're not going to get a lot of hand calculation on gate leakage. It's just a little bit too complicated to model well. Okay, another non-ideality is not a specific one to a specific transistor, but rather it's something that we as digital designers do have to be more and more aware of these days, and that relates to process variation. And what I mean by this is that devices right next to each other can have different parameters. Specifically, they can have different threshold voltages, W's, L's, etc. Okay, so you normally design your transistor for, let's say it's 1 micron divided by 45 nanometers or 50 nanometers, and when it comes back from the foundry has limited accuracy in terms of its lithography and so on, and it can't guarantee that it will be 1.00000 micron wide and 50.00000 nanometers long. There's going to be some variation on that, right? Maybe it'll be 1.05 micron by 53 nanometers, something like this, right? And then the one next to it also won't be the same. There's going to be some variation. So the variation between these devices turns out to be extremely important in matching for analog circuit design, and it also turns out to be extremely important, particularly threshold voltage variation in subthreshold digital logic. So let's I just want to introduce this as a topic. We're going to talk about it more later on in this course, but let's just say that it's very important at nodes below 45 nanometer or for subthreshold logic. And again, the reason it's particularly important for subthreshold logic is because subthreshold logic has this exponential dependency on threshold voltage, and this can really cause path delays in your digital systems to vary significantly if there's any process variation happening. The last one I want to talk about is temperature dependence. As you noted, we had the thermal voltage show up in a few cases here. There's other parameters that are temperature dependent, so we can say many parameters. For example, mobility, threshold voltage, thermal voltage, etc. change often, unfortunately, non-linearly with temperature. Okay, so I'm not going to say much more than this other than it's important to be aware of and design for this. Okay, so we can't just assume that when we create our chip, it's going to work at 25 degrees Celsius for the lifetime of that device, right? Obviously, we use our mobile phones when we're outside. You know, maybe here in San Diego, it doesn't have a whole lot of variation, but if we go to colder climates, absolutely it has variation. If we go to hotter climates, it has variation, and so on. If we're designing these devices for automotive applications, you can bet there's a huge amount of variation, or military applications, there's possibly even more variation over which your device has to work over. So the message that I'm trying to say here is that as designers, we have to be aware that temperature is a variable that is not constant and could potentially change. And as a result, we typically do have to simulate our devices in response to various temperatures and process variation and all of these other non-idealities that we've introduced. We will talk in more depth about process and temperature variation later on in this course.